Okay, greetings. So welcome to this session. So if you recall, we have looked at step 4, right, in the construction of the root locus, wherein in step 4 we looked at the notion of breakaway and break-in points. So let's continue from there and let's go forward, right? So what is step 5? Okay, step 5 has to do with what are called angle of departure and angle of arrival. Okay, from complex open loop poles and complex open loop zeros. So let me illustrate what this step is about, and then we'll figure out whether this step is applicable here. Okay, so in this particular problem. So what is this angle of departure? Like, so suppose this step applies, like only when we have complex open loop poles and complex open loop zeros. Okay, so as a result, let's consider an example. Let's say we have the S-plane, and let us say we have a pair of complex conjugate open loop poles. Now, the question is, we ask the same question, right? Because as we know, from each open loop pole, we are going to have a branch. So the question that immediately arises is that, like, what is the direction in which this branch will go, right, from this open loop pole, right? So we reasoned out when the the open loop poles lay on the real axis, but however, when they lie on the when they are in the complex conjugate plane, all the directions are possible, right? So there is an infinity of choices, right, between 0 and 360. Okay, so that's something which we need to be aware of, right? So this is what is called angle of departure. So now I hope it is clear why it is called angle of departure, right, from an complex open loop. That is, we are trying to ask ourselves as to what is the angle at which a branch of the root locus will start, like from a real open loop pole. Okay. Similarly, if you have a pair of complex conjugate open loop zeros, we know that a branch has to terminate at an open loop zero, right? The question is, once again, from which direction will it come and terminate? All right. So that's why when we talk about open loop zeros, we talk about angle of arrival, because a branch of the root locus arrives at an open loop pole. Okay. So of course, step 5 is applicable only if we have complex conjugate, complex open loop poles and complex open loop zeros. All right. So, but in our case, in our problem, right, we don't have complex conjugate open loop poles and open loop zeros, right? So we don't need to calculate angle of departure and angle of arrival in this problem. But however, for generality, I will tell you how to do this. Okay, we essentially do it this way. So what is the formula? Once again, this comes from the angle condition. The angle of departure from an open loop complex pole, right, will be equal to 180 degrees minus sum of the angles made by the vectors from other open loop poles to this pole, okay, plus sum of the angles made by the vectors from open loop zeros to this pole. Okay, so that's how we need to calculate it. So as I said, in this case, like, it won't matter, but let's say we have another example wherein we had this to be the case. Okay, so then what we do is that we draw vectors, okay, from each. This is an open loop 0 to the open loop pole in question. Let's say we call this angle as some θ1. We draw another vector from this open loop pole to this complex open loop pole that we are considering. Let's call it a phi1. okay, and we draw a vector from this other open loop pole to this open loop pole on the question, and we call it as phi 2, okay. Then the angle of departure according to that formula is going to be 180 degrees minus the angle of the vectors drawn from other open loop poles to this open loop pole, which are phi 1 plus phi 2, plus the angle of the vectors drawn from the open loop 0 to this pole, okay, which will be theta 1. Okay, so this is how you need to calculate. Okay, so I hope it is clear, right, how we calculate the the angle of departure from the open loop complex conjugate pole. Okay. Similarly, the angle of arrival is calculated by a complementary formula. Okay, that is going to be 180 degrees minus sum of the angles made by the vectors from other open loop poles, other open loop zeros to the 0, plus sum of the angles made by the vectors from open loop poles to the 0. Okay, so that is the formula for angle of arrival. Okay, so this is the general formula, but as I mentioned, this step does not apply in this example. Okay, so suppose if we encounter such a case in a problem, you can just write that this step does not apply in the problem understood. Okay, in this problem, because there are no complex conjugate open loop poles and open loop zeros, right, in our problem. Okay, so consequently, we don't need to do this step. But however, I just wanted to discuss this step so that, like, in case we had complex conjugate open loop poles and open loop zeros, we should do this step. Okay, so that's something which we need to keep in mind. All right. Now, moving ahead to step 6. Okay, step 6 is to determine what are called as the crossover points. Okay, what are the crossover points? These are the points where the root locus crosses the imaginary axis. Okay, so these are important points because, as we know, the imaginary axis, right, plays a very critical role, right? The imaginary axis separates the left of plane from the right of plane, right? Is it not? So the left of plane is very important because we want all the closed loop poles to lie in the left of complex plane for system stability. All right. So if we have what to say, a root locus going from, let's say, left of plane to right of plane or right of plane to left of plane, it is it is going to cross the imaginary axis. Okay, so such point where the root locus branches cross the imaginary axis, or what are called as a crossover point. Okay, so now the question is, how do we determine such point? Okay, so we know that in general, a complex variable S can be written as sigma plus j omega. The imaginary axis, as we already on the imaginary axis, the real part is 0, right? So people will immediately substitute S equals j omega, right? To characterize the imaginary axis. Okay, so many places you will see that to characterize the imaginary axis, people will just write S equals j omega, right? So that's how we look at this. All right. So consequently, what happens is that, like, if you want to determine the potential crossover point, this is what we need, right? So the closed loop characteristic equation is 1 plus k divided by s square plus 4s equals 0. Okay. So see, obviously we want to figure out where the closed loop poles will cross the imaginary axis, right? So if you simplify this, the closed loop characteristic equation will become s square plus 4s plus k equals 0. So this equation, as we know, characterizes the closed loop pole, right? Now, if we want to find potential crossover points, what we do is we substitute s equals j omega in this equation. So what will happen to s square? What do you think will be j omega whole square?
Minus omega.
It will be minus omega square, right?
Yes.
See, j omega whole square will be j squared omega square. J squared is going to be equal to what to say? Is going to be equal to minus omega square. So essentially, what will happen is that we are going to have minus omega square plus 4 times s. You substitute for s j omega, we will have j omega plus k equal to 0. Right now, we see that there are two unknowns in this equation, right? Omega and k, right? So how do we solve two unknowns from one equation? Please note that this has both real and imaginary parts. So although at first glance it appears to be only one equation, actually there are two equations. Okay, so if a complex variable is 0, the real part should be 0, the imaginary part should also be 0, right? So we segregate the real part and the imaginary part. So both the real part and the imaginary part should individually be 0, right? So this one we'll have, right? So the real part is minus omega squared plus k, that should be equal to 0. The imaginary part is 4 omega equals 0. So 4 omega equals 0 gives us omega equals 0 as the only solution. And when I substitute omega equals 0 in this equation, what will I get for k? K equals 0, right? So this implies that omega equals 0 or s equals 0 at where k equals 0 is the only crossover point. But this seems to be very trivial, right? But not quite so, right? What do we get out of this? We are going to shortly discuss. Okay. So if omega equals 0, this means s equal to 0, right? Because s equals j omega. We are considering points of the form j omega when we are dealing with this stuff, right? Is it not? So we are talking about the origin. And that is obviously a crossover point in our case because there is an open loop pole at the origin, right? So one branch of the root locus starts from the origin. So what do we get out of this derivation and this step? It just so turns out that this step shows that the root locus branches do not cross elsewhere, okay, other than at s equals 0. Okay, they cross only at s equals 0, and there are no further crossover points. Okay, so that is the implication, okay, of this particular step. So I hope it is clear, right? So how we got this particular step, all right? So this essentially these constitute the 6 main steps, okay, of the root locus. Of course, the 7th step is to sketch the root locus, easier said than done, okay, because it says that choose a lot of test points in the broad neighborhood of the origin and imaginary axis, and then sketch the root locus. So nowadays we have computational tools to do that. In fact, in MATLAB there is a command called rlocus, okay, which will essentially plot the root locus for us, okay. But before we had computational tools, people used to calculate in the vicinity and then plot the root locus because we need to essentially consider the vicinity of the imaginary axis for stability these purposes, okay. So that is why that step has been showcased. But when I ask you to do a problem on involving root locus, please do steps 1 to 6, okay, and then plot the root locus. So let's plot the root locus based on the knowledge squared from steps 1 to 6. So we first plot the two open loop poles in the S plane. So the root locus branches start at the open loop pole as k tends to 0. So one branch starts from 0, one other branch starts at -4. Then what happens? The two branches start going towards each other, and then they intersect at -2. Okay, -2 is a breakaway point. What was the value of k at -2? Do you recall? We just calculated, right? What is the value of k at -2?
4. 1.
No, if you go up, we calculated the value of k at 4, right?
4.
4, right? Yeah. So we can see that the value of k at -2 is 4. Okay, so that's what we have. Then what we have the two branches breaking away from the real axis. Okay, and going up. Okay, as k tends to infinity. So these are the two branches that have, they essentially go towards asymptotes along the whereas they go to infinity, they explain along the two asymptotes, right? So one question which may immediately come, hey, will they go as straight lines or curves and so on? Yes, we are just plotting an approximation here. Okay, so if you want a very accurate description, we need to use numerical tools. Okay, so but we get the point, right? So essentially we have an approximation, like wherein we are able to get the approximate trend of the closed loop poles, okay, using the analysis that we have done. All right. Okay. So any questions? So this is the root locus. All right. So any questions on this? So immediately we can see that the closed loop system is stable for all k greater than 0, right? So anyway, that we have already established by Rolle's criteria, but we are from the root locus we are re-establishing it because for all k greater than 0, we can immediately see that both the branches of the root locus lie in the left off plane, right? If both branches lie in the left off complex plane, then the closed loop system is stable, right? Is it not? So that way we are essentially having. All right. So any questions on this till now? Okay. So now we are going to see how we can use root locus to our advantage, right? And sort of like figure out how we can get the ranges of the gains, right, or the parameter k that will ensure that we meet performance also. So do you recall this derivation wherein we essentially converted the or this problem, right, wherein we converted the performance specifications into desired regions of closed loop poles? Yeah, this problem, right? Yeah. So wherein, if you recall how we converted the performance requirements of settling time less than 4 seconds and peak overshoot less than 10% into this sort of this open trapezoid region, right? So we are going to use the same thing here. Okay, so so I'm just going to draw the same feasible region in the root locus plot now. Then we will understand the impact of root locus. So if I am drawing the that open trapezoid here, so this is sort of the diagram, right, that we have. This passes through . right? So we already are aware of, right? This is also 53 points. All right. So now the question is, what sort of parameters will ensure, what range of gain k will ensure that our performance metrics are also satisfied. So now we can see that there are some critical points here, right? So let me call this point as point A, okay? This point as point B, and this point as point C, okay? So we can immediately observe that when my root locus crosses the point A, right? One of the branches crosses the point A. From that time on, or from that instance onwards, right? For all subsequent value of k, till the root locus branches hit B or C, I am going to have both branches within the open trapezoid, right? Isn't it? So let me point out once again. So let's say I increase from k equals 0, right? This branch, which starts from 0, keeps on going, and at point A cuts the vertical line at -1 and gets into the open trapezoid, right? From that instance onwards, for all subsequent values of k, till I hit the points B and C, okay, on the slant line, I am going to be having both branches of the root locus in the performance feasible region, right? Isn't it? Or the feasible region of closed loop poles corresponding to performance requirements. So those are the things that we need to look at. All right. So I hope my argument is clear, right? So so how do we do this? So at point A, how do we find the value of k? So for that, once again, we use the closed loop characteristic equation, right? The closed loop characteristic equation is 1 plus k divided by s squared plus 4s. So k is going to be anyway s squared plus minus of s squared plus 4s, right? Is it not? Now, how do we get the value of k at point A? So what is the value of s at point A? It is -1, right? Is it not? Okay. So does everyone agree? Because when I hit point A, when one branch of the root locus hits point A, what is the value of s there? It is -1, right? So you can see that. So if I substitute -1 here, what is the value of k that I will get? I will get
3.
3. So at point A, the value of k is going to be equal to 3. So what it means something interesting, right? For all k greater than 3, I get both my branches of the root locus into the open trapezoid. But they don't remain there forever, right? Because at point B and C, I go outside the trapezoid, right? So we need to figure out what happens at point B and C. So the question becomes, like, how do I get the values of k at point B and C? Okay, we follow the same step, but however, we make use of the fact that the root locus is a mirror image about the real axis. So it is enough if I calculate k at point B. Okay, the value of k at point C will be the same, because as we know, for polynomials with real coefficients, the roots occur as complex conjugate pairs, right? So if I have a root at point B, the corresponding conjugate will be at point C. So the value of k will be the same. Okay. So now, how do I find the value of s at point B? I need to substitute for s, right? Yeah. How do you think I can find out? It will be, the real part is -2. What do you think will be the imaginary part? Do you agree? It will be 2 times 53.7, sorry, 57.33. Correct? How do we get this? because we need this as the imaginary part, right? This angle is 53.77. This distance is 2, right? So tan theta is opposite by adjacent, correct? So the opposite side will be 2 times tan 57.33. I hope that is clear, right? So if we simplify this, we will get minus 2 plus 2.73 J. All right? Okay. So if we now want to find K at point B, we have to essentially figure out minus S squared plus 4S at S equals minus 2 plus 2.73 J. Okay, this I leave it to you as an exercise to do. If you do this, you will get the answer as, please do this, okay, you will get the answer as 11.4. Okay, so this I leave it as an exercise. You just need to substitute. I hope it's clear what I'm doing, right? So since those points lie on the root locus, the easiest way to calculate the value of K is that like you substitute the corresponding value of S, okay? And then like you get the value of K. That's about it, all right? So you essentially can get the value of K. And so consequently, what we do is that like we essentially substitute and then like find out, you know, like how it will be what to say, we will be able to get this value of K, right? So I also leave it as an exercise that K at point C will be you can double check for yourself, right? It's going to be the value of minus S times S squared plus 4S, that S equals minus 2 minus 2.73 J. That will also be the same. Okay, this will be 11 points. So at points B and C, the value of K will be 11.4. So this is something which is very interesting, right? So we can immediately see from the root locus that beyond K greater than 3, okay, we are going to have the settling time criteria to be satisfied, okay, because both my root locus branches will be to the left of the vertical line at minus 1, okay, point number 1. Now, beyond K, value of K greater than 11.45, I will not be able to satisfy the peak overshoot condition, right? So I will be able to satisfy the peak overshoot condition only till 11.45, right? So that is a very interesting observation, right? Is it not? So that is something we are going to utilize, okay? In our analysis. So consequently, if we look at this, putting both these things together, right? The performance requirements would be satisfied that is both performance requirements, okay? So that's why I have written in plural, okay? Both performance requirements would be satisfied for K greater than 3 but less than 11.45. Okay? So this is a very big result, right, from this analysis. All right? So we have been able to essentially achieve the fact that, you know, like we have been able to get a region of K, you know, like wherein we will be able to ensure that the performance requirements of settling time less than 4 seconds and peak overshoot less than 10%, okay, would be satisfied. And what is the impact of this entire analysis? Please note that initially our K went from minus infinity to plus infinity. Then we did stability analysis. All right. For stability, what did we say? Hey, we wanted k to be greater than 0 for stability. So using the Route's criteria, we could essentially narrow down from minus infinity to plus infinity, from 0 to infinity. But still, that is a big region, right? Is it not? Then what did we do? We looked at this performance metrics and we said, okay, look, like we will identify a further subset, okay, in this set for performance. Okay, so imagine that, like this is a practical system, right, that we are working with. All right, someone asks us to figure out the value of k. What we have done is that using the tool that we have learned, right, which is the root locus, we have first looked at, like how do we get the root locus, like for the system, and then use the root locus to narrow down, like the region of the parameter k, which is a design parameter, that will also ensure that the performance requirements are satisfied, right? So this is a tremendous advantage, right, as far as the design process is concerned. So just to reiterate the impact of what we have done, initially we start from k between minus infinity to plus infinity, right? That's a big range. So using Route's criteria, we shortened it to 0 to infinity, but it's still a big range, right? But using root locus and performance criteria that we have discussed, we narrowed down this to 3 to 11.5, right? So this is a relatively smaller range. Now I can go to the practical system, right? And then fine tune in this range, 3 to 11.5. Then I know that with reasonable certainty, I will be able to stabilize the closed loop system and also achieve the performance that I desire. Okay, so that is the advantage, okay, of this particular process. Okay, I hope the process of this control design using root locus is clear. All right. Okay. Any questions? Okay. So I suggest that you work out this process once again, okay, on your own, so that you will also be able to understand the steps, final steps, and we'll do more problems, okay, as we go along in your homework and projects, which will clarify this process further. All right. Okay. So any questions on the steps involved in the construction of the root locus and how we can use root locus for control design? All right. Okay. So if not, I will close today's session here, and then like we will continue in the next class. Okay. Thank you.